So we can represent this equation graphically. And the graphical representation would be something like this. So along the y-axis, you've got time. Along the x-axis, you have space. And suppose that this is your initial position, x prime at t prime. And this is your final position at x at time set t. And in between, there is another time slice, which is t double prime. So what this equation is saying, let me copy and paste this equation. So what this equation is saying is that, we can propagate the system from here to here, but to propagate it, we first have to evaluate the propagator to all the middle points. And then multiplied by the propagator from those midpoints to the final points, and add them up. And we do then an integral, okay? So this is what graphically this equation means, okay? Because we are doing an integral over the intermediate time and space. So at the intermediate time, we're integrating over all of space. Okay? So now what if we kept on doing this? What if we kept on doing this over and over again? So to do that, let me just, denote the initial time, denote initial, coordinates, say, by, say, x1, t1, and denote the final coordinates by xn, tn. Okay, and what we are doing is that we will subdivide the interval tn to t1 into n minus 1 equal times, equal time steps, or equal length time steps. Length intervals. So these intervals are, say, tn minus t n minus 1. It'll be delta t, and that'll be given by big Tn minus T big N minus T1 divided by N minus 1. Okay? So all that we're doing is that we're just dividing up this time into smaller pieces. And at some point, we're going to take N to go to infinity. Okay, so then what does the picture becomes? If I insert this identity at every of these intervals, what is it? Let's draw the picture first, and then we can write down the expression. So this is our initial. Suppose this is x1, and this is the final time slice. Say this is xn, and I'm just going to draw a finite number. It's easy for me to draw it like this. These are all the small time intervals. And so what we're going to do is that we are going to take, this is probably will be one example of a, of a path. Oops, sorry. So what does this picture actually represent? What it represents is the following. So if I take the propagator from xn, the final time xn tn, final coordinate, and the initial x1 t1, we insert in it n minus 1 intervals. So dx n minus 1, dx n minus 2 dot 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 dx2, and then we have xn tn xn minus 1 tn minus 1 xn minus 1 tn minus 1 xn minus 2 tn minus 2 dot 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 all the way down to x2 t2 x1 t1. Okay, does it make sense? I mean, this formula, of course, is very easy to see, but this picture that we are actually having to integrate over all these paths.
Sir, I get what's going on, but why are we doing this? Like, what's the end goal here?
Oh, yeah. The end goal is to get a completely different formulation of quantum mechanics.
I see.
Yeah, the end goal is that we want to find an expression for this thing for a very small time interval, and then take Dirac's idea seriously and see what comes out.
So, like, how small can t become? Like, the del t become? Can it like infinitesimally small or?
Oh, okay. Infinitesimally small.
Yeah. Okay. Got it.
Yeah. Okay. Good. Okay. So now let's see. Now let us take one of these small propagators. Okay. So let us take, one of these factors. And suppose we take x small n, t small n, xn minus 1, tn minus 1. Okay. Now, according to Dirac, this corresponds to the exponential of the I by h of the action of Sn n minus 1. So by this, I mean the integral from tn minus 1 to tn dt prime, or dt, let's just call it t. And then, the classical Lagrangian with x and x dot. Now, the idea is that, when we look at this integral, these, we can give you these boundaries, the time intervals, but that does not completely tell you what this integral is. You have to choose a particular path. It's only after you choose a particular path that you can do this integral, and so this this action has a particular value once you're given that path. So even though I'm writing the action as a function of n and n minus 1, it's only specified after I give you a particular path, which starts at tn minus 1 to tn. So if I go back to my picture, so suppose that this is tn minus 1, this is tn n. So there are many paths, right, that go from here. So what we have to do is that we have to choose one of these paths and take choose one of these paths. So if I choose one of these paths, then I can plug that into my Lagrangian, the x here, and then evaluate the Lagrangian, and then do this integral, and then we'll have this action. Okay? So now what we're going to do is that, suppose that we have like chosen such a path, and for that path we got some, for some action, and then we get e to the power ih s n minus 1. Now for that particular path, so we have, let's just color that path a different color. So for that particular path, we can then evaluate all the exponential of the action. Okay? And because each of these things are multiplying of each other, so what we have to do is that we have to multiply all these different actions, exponential of the actions. So here, n goes from 2 to n. So of course, because it's a multiplication and there's an exponential, we can write it at e to the power I by h, sum over n, going from 2 to big N, s of n minus 1. But this is nothing but e to the power I by h, s of big N 1. So this is the action that corresponds to this particular path. Okay, sorry, I'm going to erase this little, arrows, these tick marks, because otherwise it just creates confusion. Okay, so for this blue path, this is the contribution a la Dirac. Okay, but the thing is that, this is just one contribution, right? It's just one contribution to xn, tn, x1, t1. We are missing the contribution from all these other paths now. So to actually write equality here, we should, well, I'm going to write the Wigley's proportionality. This is my proportionality, because there's a dimensional constant that we will add. So, but we cannot put this thing equal to this thing. What we can do is that we can say, okay, we have e to the power I by h bar s of n minus 1, but we sum over all the paths. All the paths, and for each of these paths, we evaluate this thing, and we sum over all of this. Okay? And so how did this sum come about? This is an assumption. Okay, this is an assumption because remember, so for example, if you're doing quantum mechanics and you are doing a double slit experiment, so what do is that you basically say that, okay, there is an amplitude. So if you calculate the amplitude of the particle, going in this direction, then you add to it, and so that's path number 1, and this is path number 2. Okay, so the amplitude is going to be the amplitude of the path that the particle takes in path number 1 and the amplitude that the particle takes in the path number 2. And when we're doing probability, we are going to have this amplitude squared, and that's going to create the interference pattern that we see. Because in quantum mechanics, whenever you have like two independent ways of things happening, you have to add the different wave functions or the amplitudes, right? I mean, similarly, say in the Stern-Gerlach experiment, you can have, well, it's everywhere in quantum mechanics, right? You can have two different alternative things that can happen, and you basically have to add up their contributions. So this is basically the motivates summing over all the different paths.
Sir,
okay, so
will this summation be in front of the exponential or in front above the exponential? Like, is it a kind of a product of all those?
Sorry, you're breaking up, Hanahi. Can you repeat that?
I mean, sir, will the sum be in front of the exponential or above it?
It'll be in front of the exponential, because what is happening is that each factor within the sum represents the amplitude for one of these paths. And all these paths are, basically they're mutually exclusive in, classically, right? These are all alternatives for the path to take. And that's what we do, so you can actually apply this to the double slit experiment, and you can see that you get the right interference pattern. So Feynman also tried those things, okay? If you look at Feynman's book on path integrals, he talks a lot about the double slit experiment. Okay, is it clear why we are adding all the paths?